So this is my video for test 4, and getting started, we need to find one organic compound with three functional groups that must contain an oxygen containing functional group, nitrogen containing functional group, and one other functional group, and name them. Also, every atom in the structure, identify each atom's electron geometry, molecular geometry, and hybridization. So the molecule that I've gone with is serine, and that is drawn with an HO over here. Carbon, 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 with a double bonded O and a single bonded NH2 group right here. So let's start off by figuring out which way we're going to go. Well, actually, we'll number it at least. So 1, 2, and 3. Oh, and I forgot the hydroxide group right there. But okay, so 1, 2, and 3. 1, 2, and 3. So let's identify our functional groups. Well, I can see one already right here. And I know that's a carboxylic acid. I see another one right here, which I know is an amide. And I see another one right over here, which I know is an alcohol. So let's try and name this entire molecule real quick. So it's best for us to actually go in this direction. So 1 being carboxylic acid, 2 being the amide, and 3 being the alcohol, because the carboxylic acid has the most priority over the alcohol. And we have to start at one of those sides. We can't start with the amide, so we'll start with the carboxylic. But that doesn't actually go in, that actually doesn't start the entire compound name or molecule name. The molecule will start with the amide actually. So that's on the second carbon. So 2 amino. And then the next group would be this alcohol over here. So we'll do another dash. And 3 hydroxy. So the hydroxy so usually we're used to an OL suffix from this, but because the carboxylic acid takes more priority, we're going to have it as a hydroxy instead. And then from here, what's our longest carbon chain? Well, we have a 3 long carbon chain. So we know that 3 long equals to a propyl. So we'll have prop as our parent. And then, because of the carboxylic acid, like I was saying before, now this comes in and we have a propanic acid. So that is the entire name of, or that is the IUPAC name for serine. So then let's go through our molecular geometries. We'll start over here with this alcohol O. So first we have the O on the alcohol group. And so our electron geometry is going to be tetrahedral, because on that O we have a singular bond going back to this carbon, and then we also have 2 lone pairs, and then we also have another H. So we will just keep it as a tetrahedral for the electron. But for the molecular geometry, and our electron geometry here, our molecular geometry here is going to be bent at an angle less than 109.5. because 109.5 is the ideal angle, and we have it less than because these two lone pair groups are going to cause it to be smaller. So molecular geometry is less than 109.5, and our hybridization is going to be sp3 because we have 1, 2, 3, 4, and the electron geometry or the hybridization depends on bonds and lone pairs. So we have sp3. So then we'll go to carbon 3 next. So that's going to be this one right here. So for carbon 3, we are going to do electron geometry, molecular geometry, and hybrid. So for this one, we have that makes it look like it has a bond right there. It does not. So it's going to the oxygen, it's going to another carbon, and then it will have 2 hydrogens on it. So it will be tetrahedral as well. And it's going to actually just continue to be tetrahedral. Hedral 109.5. Because it just has all bonds. It doesn't have any lone pairs. And our hybridization is going to be the same as the one before with sp3. Now we're going to move on to carbon 2, which if we look up here, carbon 2 is right here. And it is bonded to another carbon, the amide group, and then also another hydrogen. So our electron geometry is going to be tetrahedral. Our molecular geometry is going to be tetrahedral 109.5. And our hybridization is going to be sp3 as well. So these two share the same diagnostics. So then we'll do the nitrogen in the amine group, So let's look at it up here. So it's connected to 1 carbon, 2 hydrogens, and it has a lone pair. So it's going to have a electron geometry, molecular geometry, and a hybrid of tetrahedral because it has the 4 areas of electron density. So it has 1, 2, this is 1, and then 2 hydrogens. But it is only going to be trig pyramidal in molecular geometry because we are no longer counting the lone pairs. And then we are still going to have another sp3 hybridized. So then let's go over here and let's look at C1 now. So we're right here. So C1 is connected to a double bond with the oxygen, a single bond with the other carbon that's on the amine, and then there's amide, and then there's also this one right here to this hydroxide group. So we are going to have I'm going to put C1, and then electron geometry, molecular geometry, and hybrid. Sorry, I forgot. So our electron geometry is going to be trig planar because it only has the 1, 2, and then this counts as a single bond. So we're just going to, for the purposes of naming the geometry, it's just, we're going to count that as 1. So trig planar. And then our other geometry is going to be trig planar as well, because we don't have any lone pairs, so it won't be affected. And then our hybridization is going to be sp2. And I forgot to mention that this will be a 120 degree, and this one will actually be a less than 109.5 because we have the lone pair right here. So then let's go to the double bonded oxygen. So that's this one right here. And so we are going to have a trigonal planar because we have the one bond right here, one bond to another atom, and then the two lone pairs. So the electron geometry is trig planar. The molecular geometry, however, is going to be bent because of the two lone pairs. And our angle for the bent is going to be at 120. And then our hybridization is going to be sp2. So then our last atom is going to be the oxygen right here. And so oxygen on the end. So our electron geometry, molecular geometry, and hybrid. Well, we see that it's going to have two lone pairs, and then it's going to be connected to a carbon, and then it's going to have a connection to also another hydrogen. So it's going to have a tetrahedral. But it's actually going to be bent, and it is going to be less than 109.5. And our hybridization is going to be sp3. Jumping to the next question, we are going to draw and name 4 constitutional isomers of CH4H7Br. One should have a complicated substituent. Exclude any alkenes. So a constitutional isomer means that it is going to have a different structure, but it is going to have the same formula. So if we want it to be C4H7Br, well, the easiest one is going to be just drawing the cyclo right here, with these all being carbons. So we have our 4 carbons taken up, and then we'll just do a little Br up here. And then it's also implied that all of these have 2 H's on them down here. These all have 2 H's, but I won't go through that. So that's our first one. And we are going to start off with, so technically this is on the 1, 2, 3, and 4, but those aren't necessary in this case because it's implied that it's on the first one. So if it's already implied, then we don't need to state that. So we're just going to say that it's bromo, cyclo, butane. Because we already know that this is going to be a cyclo group because it's all connected to each other like that. And then 4 carbons all connected is bute, and then it doesn't have a functional group, so it's just going to be butane. So then the next one would be just drawing out like a little thing right here. And so that's going to be so there's going to be a carbon here, and carbon here. And then we're going to do just a little thing up like this, and then over here. Oop, I didn't want that. So up there, and then up there. So we have 1, 2, 3, 4, and then we'll have another one here, and then we'll have 3 more up here. So, and I need to make sure I put that. So we're going to have, again, this is thought to already be on the 1. So we're going to have bromo, methyl, because this right here is a methyl group. And then, again, we just have another cyclo. And then this is the longest continuous chain right here is going to be 3, which is a prop. So then we have prop and no functional group ane. So propane. So then we'll go on to the next one. And we'll draw another triangle for the cyclo. And we'll do a CH3 up here and a BR down here. And so this one we actually will have to make sure that we have 1, 2, and 3. And in order to know which one goes first, we look at what their names are. So this is another methyl group. And this is another bromo. So the B comes before the M. Therefore, we have 1 bromo, 2 methyl, cyclo, propane. And then for our final one, we'll just have another triangle. And then we'll do a 2 little things up here, or 2 bonds up here, and we'll have the BR, and we'll have the CH3. And so again, this is thought to just already be stated on the one. So there's no need to necessarily say that it is there. But we'll just go ahead and say 1, 1, so that we know that they're both on the same thing right here. And this will be 1, 1, bromo, because that comes first again. Bromo, methyl, cyclo. Sorry, this is because I ran out of space. Cyclo, propane. Note, we don't need this here normally. It's only because I ran out of space writing in this direction. You only use a dash whenever there's a number, usually. So, just want to make that clear. Now we're going to show that phenyl has a more acidic proton than cyclohexane. So let's think about this. What does phenol look like? Well, phenol looks like a hexane. Oop, that's going to end up being an octane. Oh, that's another octane. So it looks like this, and then we're just going to have a double bond here, a double bond here, and a double bond here. And we will have an hydroxide, or we will have a hydroxide group up here. So this is phenyl. And then for the cyclohexane, we'll have another hexane right here. And then we'll just do a little OH at the top. So, but that's it. So they don't look all that different, right? But in order to find out which one is the most acidic, we look at the conjugate base. So that means that we're going to remove a proton from our hydroxide group. So let's just go down here, minus an H plus, minus an H plus. And so I'll just copy and paste these down here just for the ease of it. And so we're going to have an O with a negative charge on it. And we're going to have something that looks similar. So I'll just paste it down here again. But remember, we won't have these double bonds inside. They don't just all of a sudden appear. And we'll have an O again with a negative charge. And again, they don't look all that different, but they end up becoming very different whenever we start looking at resonance, because now we're looking for resonance. Do they have resonance in their conjugate bases? Well, let's see. So I can go ahead and already see that we can have one here, because we can take this right here and then we can move it over here, and then that's an open spot. So let's go ahead and draw that resonance. So I'll just go ahead and paste it again. Why not? So instead, we're going to get rid of this right here, Then we're going to have a double bond right here because that double bond comes up here and allows us to share the electrons between the O and the carbon beneath it. So now we just have two lone pairs up here. So this is no longer negative. But because of that, we now have two lone pairs over here, or a lone pair over here. So we're going to have a negative sign on this carbon. So we still have our negative sign, and we still have, it's essentially the same in terms of formal, or it is the same in terms of formal charge. We've just created a different bond up here. So then we can continue and show that we can just continue moving these around, right? So now we can go with this lone pair right here, and we can move it down to here, and then we can move this into a lone pair over here. So then, again, I'll just go ahead and paste it again. So this is what we had before with the O. And then now, instead, we're going to have a double bond right here and the lone pair over here so that we have a negative charge right here. So that's another resonance structure. And so we can do this again with this being one arrow to right here. And then we can move this up here. So now, just go ahead and paste it again. Now we have an O right here. Get rid of this one, put it right here. Get rid of this one, put it right here. And then now we're going to have this lone pair up here on this carbon. So as you can see, we at least have 1, 2, 3, 4 resonance structures. Now let's see if the cyclohexane has any resonance structures. Does it? Well, no, it really doesn't, because if we want to use one of these down right here, well, that changes our formal charge, so it's no longer the same. It no longer has the same structure. So because of this, we are going to say that this has no resonance. Resonance. So if we want the conjugate base to be more stable, well, which one's more stable? The one that has 0 resonance or the one that has at least 4? I'm going to take my bet and I'm going to place it on this one right here. So I'm going to say that phenol is the more acidic proton. So that should be that one. Moving on to the next. Now we get to draw the conformations or chairs for molecules of our choosing. So one of the ones that I chose, or I guess it's the same across both, but anyway. So this one right here, where we have a wedge with a CH3, a dash with a ethyl group, and another ethyl group right here. So if we go ahead and number these 1, 2, 3, 4, 5, 6, we can't number it the other way because then it would be 2, 3, 4, 5, 6, and that's much. We want the lowest numbers, so we know that it has to be 1, 2, 3. Now let's just go ahead and name it real quick. So we know this is a methyl group. Methyl, ethyl, ethyl. Let me just go ahead and color that in real quick. So let's just go ahead and name it. So which one will come first? Well, the ethyl group will come first because it has an E and not an M. So it'll be, and it's at both 2 and 3. So we'll do 2, 3, diethyl, 1, methyl, cyclohexane. Because we have 6 in the longest carbon chain, and so there's no functional group, so we're just going to call it hexane. So if we know that a dash, or sorry, not a dash, if we know that a wedge means up and a dash means down, then we have one going up here, one going up here, and one going down here. So 2 up, 1 down. So let's go ahead and draw this on the chair. So let's go ahead and draw our chair like that, like that. And so we'll call this 1, 2, 3, 4, 5, 6. And it'll just, and so we're going to start with one that's going up, down, up, down, up, down. Really 4, 5, and 6 we won't need because we only have groups on 1 through 3. So let's go ahead and check this out. Methyl on the 1, and it's going up because it has the wedge. So if it's going up, then it's going to be on the axial right here, so CH3 for the methyl. Then on this one, we have an ethyl that's going down, so it's going to be on the axial as well, so CH2, CH3. And then on the third one, it's going up, so we're going to have another one that's on the axial because it needs to go up as well, so CH2, CH3. Sorry, I'm just writing these in pink in a different color because they are hard to see whenever they're going through white, so I just want them to be easily recognizable. So now let's see, what do we have? So I think we can make this more stable because generally whenever we have them in the axial positions, they want to be in the equatorial. So let's just go ahead and do the chair flip real quick. So if we do the chair flip of this, so boom, 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 boom. That is an ugly chair, but it'll work. So whenever we do a chair flip, the axial becomes equatorial, and the equatorial becomes axial. And so this is going to continue to be our 1, 2, 3, 4, 5, and 6. Again, 4, 5, and 6 aren't really necessary, but just for the purpose of having them, I'll leave 4 because I can't get rid of it. So let's see. So instead of it being up on the first one, we're actually going to have an axial down, then up, then down, then up, then down, then up. So everything that was axial becomes equatorial. Well, all 3 of them over here were axial. So let's just go ahead and make those equatorial. So equatorial is going to be CH3. Equatorial here is going to be down, and that's going to be CH2, CH3. And this is going to be up, so this is going to be CH2, CH3. So let's just make sure that this makes sense. We need this one to be up, and we need this one to be up based on this, because those are our 1 and 2 groups. So 1 and 3 groups, sorry. 1 and 3. Well, if we need those to be up, well, that makes sense now because our axial is pointing down and our equatorial is pointing up. And then we need this one to be pointing down, the axial is pointing up, and the equatorial is pointing down. So it checks out. We're going to have it like this. And so if we just get rid of all these stray lines, then we can see that these are all axial. So this is going to be generally more stable. Just from the get-go, we can already tell that because we have an axial, axial, axial. Or no, sorry. Equatorial, 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 not axial. None are axial in this one. So then the next one I did was mostly, actually, we'll just go to the next page for this one, just so I have enough room. So the next one I did was mostly the same, except I just flipped this one to being upside down, or to being down, and then this one continued to be down, and then this one continued to be up. Let's color that in so we know it's up. So up, 1, or again, we're going to go back up here and just make sure. Up is wedge, down is the dashes. So we have 1 up and 2 down in this case. So let's go ahead and draw our chair. Again, not the prettiest chairs you've ever seen, but they will do. So 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Continuing. So our 1 is going to be down. We know that from the dash. So we have a down. So instead of going up like that, we're just going to draw this, and we're going to have one going down, CH3, that methyl group. And then now, on the second one, we're going to have it going down as well. So that'll stay on the axial position. So that'll be CH2CH3. And then this one is going to remain the same, and that's going up. So we're just going to put that one on the axial as well. So this is going to be CH2CH3. So then let's draw the chair flip. A little chair flip right here. Let me just add some extra space. So then just going in the opposite direction with the chair. Oof, that one's pretty bad. Again. Oh well. So again, axial to equatorial, equatorial to axial, and it should also follow the same thing up here as being down and up. So if our CH3 wants to remain being down, then it'll be on here on this axial, and let's check to make sure that it flipped. Did it? Yes, because it used to be equatorial, now it's axial. So that's good. Our second, which we're going in the same direction, so this is going to be 2 right here, just for reference. So number 2 was down. Well, that's not down right now. We need that to be on the equatorial, so we need this to be down. So we're going to place our ethyl group right here on that one going down. And then let's see. So our last one is going to be another ethyl group, and it is going to need to be, sorry, this needs to be a little bit more angled. Should be a little bit angled. CH2CH3. Just want to make that clear because it shouldn't be straight down. And then our last one, it needs to be up as well, or up inverse to both of these. So if we draw ours up, this is going to be CH2CH3. And it should also have flipped from what it used to be. It was on the axial, now it's on the equatorial. So everything makes sense here. And let's see if we can make sense of this. Which one's going to be more stable? Well, let's ask ourselves, which one has more on the axial? Well, I see 1 on the axial here, 2 on the axial here, 2 axial. And on this one, I see 1 on the axial. Oh, the other 2 are on the equatorial, so we have 1 axial. So based on that alone, we're gonna have less interference between the axials. So we're gonna have this one as the more stable conformation. And that should be it. Thank you very much.